Welcome back. So the next thing we're going to look at is figures, measurements really. There's a classic example of somebody was running a race and they ran 22 meters and it took them 7 seconds, and they said, oh, I wonder how fast I went. And so they took 22 and divided it by 7, and they said, man, I ran 3.142857,143 meters per second. And they wrote down all those numbers. And that's just meaningless. You've got a really crude measurement of distance, and you have a really crude measurement of time. What's that saying is it's 7, at the very best it's saying it's 7, not 6, not 8. In fact, it's worse than that if you follow the science method. And it's saying it's 22, not 23 or 21, and it's even worse than that. You've got really lousy measurements, and yet you've got this thing that goes on to what, probably a billionth of a meter per second is your precision. It makes no sense. In math, it doesn't matter because they're just looking for numbers. In engineering and physics, it really matters. You can't take a lousy measurement of length and a lousy measurement of time and get a really precise measurement for speed. It just can't work. And so somehow we have to limit how we write an answer compared with what original numbers we put in. And that's what we're going to talk about now. So we can have quantitative things like it is hot or it is cold. And frankly, I was kind of trained to ignore those things, but my wife, who's a behavioral scientist, says absolutely not. Qualitative stuff is actually quite informative when you're really trying to find out what's going on, so don't dismiss it, which was a real shock for me. But in science and engineering, where you can build things, etc., then the tendency is more to say, you know, I want numbers. I think it was Lord Kelvin. No, probably not Lord Kelvin. Rumford. Lord Rumford said, if you don't really know about anything until you can put numbers onto it. If you're just talking about it, you don't really know about it. There's two types of quantitative stuff. There's measured stuff and counted stuff. If I say how many cars are there in the parking lot, you're not going to say 7,253.6. You're not going to have a half a car. You're not going to have a third of a car. You're going to have either it's there or it's not. They're counted things. We say they're exact. The answer is 17, not 18. It's not 17 point anything. It's 17. Then there's measured things, and it's not obvious, but the number that you write down depends upon not just the thing, but what you use to measure it with. So the deal goes like this. If I have a ruler, for example, and it's marked, and the smallest division, say, let's use the classic example, is the millimeter. So I can look along a ruler and I can go, well, that's 1 millimeter, 2 millimeters, 3 millimeters, that's 25 millimeters, 30 millimeters. I can count my way along. But at some point I'll get to the stage where the end of my object is, say, in between 13 and 14 millimeters. So I'd write down it's 13 point, and then I got to somehow guesstimate this thing. And I would say that's 13.3 millimeters. And the deal is we always have a guesstimated number at the end. Always. Even if we think it's 0, we think it's exactly on the line, we put down a guesstimated number. So ironically, I can look at any number we write down as a measurement, and I can tell you what ruler you used. If it's point something millimeters, I know you used a ruler where the smallest division was millimeters. If it is 13 millimeters, I know you used a ruler where the smallest division is the centimeter, because you guesstimated the millimeters and so on. And it doesn't matter. I could write this down as 1.33 centimeters, and it still means that it was the smallest unit was the millimeter. Doesn't matter whether I change the units and move the decimal point or what. It's what that is, that final column represents. And the final column here, in both cases, represents the tenth of a millimetre. And so in both cases, the ruler had millimetres as its smallest unit. So there's a fair amount of implicit information in how you write numbers down. And that takes a bit of practice, and we do that an awful lot in lab. We're careful about it in lab. So, for instance, this tells me that, well, you tell me, what was the smallest division on the mass scale that was used on that massing machine? It was kilograms, wasn't it? Because we have a tenth of a kilogram. We have 3/10, but the column is the tenth of a kilogram. Look at your last column. Whatever that last column is, you had the ruler or the meter, whatever, was one to the right, one to the left. So we say, when we write a measured number, we assume that the last digit is uncertain, resulting from estimation. Earlier digits are certain. They were counted, they were observed. But the last one was estimation. Reasonable people may disagree about the last digit, but should agree about earlier digits. So there's some wiggle room here. It's okay. What you can't do is you can't just put a whole bunch of numbers there that don't make any sense. And they came out of the math. That was my calculator that gave me them. So I need to figure out how I take one number and another number and figure out how to write the answer down. So we say we refer to number digits as significant digits, or significant figures sometimes called. So how do we mathematically combine these things? We use certain rules. First thing, let's figure out, let's get some talking here. How do we talk about these things? We say that number has 7 significant digits, that number has 5 significant digits, etc. How do we work that out? The key difference is if there's a decimal point or if there's not a decimal point. In both cases, the left-handmost non-zero digit is always the most significant. Left-handmost, non-zero digit. Down here, I've got one where the left-handmost digit is there. If there is a decimal point, then the right-handmost digit, no matter whether it's 0 or not, is the least. I count all the digits in between. So this would be 1, 2, 3, 4, 5, 6. That's a 6 significant digit number. Because the 2's the most, that right-hand 0 is the least, I count all the ones in between. This here, there is a decimal point, so that 0 counts. This is a 1, 2, 3, 4, 5. That's a 5 significant digit number. What about that guy? Is it 4? It's 2. Because there's no decimal point. If there's no decimal point, the right-handmost non-zero digit, that's 2. So the idea, the philosophy is if you put the decimal point, you mean all your columns, apart from the ones before the first thing. If you don't put a decimal point, these are called placeholders. These just tell you that you're dealing not with units or with tens, but with hundreds and thousands. So it's quite subtle. So this one here, what would this be? This would be 5 or 4 or what? It's got a decimal point. So what do you think? Who's going to be brave and tell me?
That one, it's all of it. Which one?
So that one, what is it?
It's all of it. 5.
So what is it?
5?
Yeah, if you write down all of it in the test, I'll say you get none of it. So you're right, it's 5. What about this guy?
3.
It's 3, isn't it? Because the 2 is the most significant, and there is a decimal point, so that 0 is the least significant, so that's 3. Whoa, don't even worry about that. Never worry about the powers, it doesn't matter.
4.
So that's going to be 4.
4.
That's going to be 4. So the power changed, but the actual number didn't change. What about this one?
2.
2. This one, 3. This one, 3. I used to be on the committee that set the exams for the Florida 6 through 12 physics teachers test. And the only two things that would cause arguments were significant digits and the scientific method. Those questions, it was just, man, it was a minefield. People have very strong feelings about these, and some people feel that you should always apply significant digits, and other people feel that you just need significant digits when you're doing practical work. But when I'm doing homework problems and the like, I want to say 7 kilograms and 5 meters. Keep the numbers simple so you can't misread them. But I want my answer to be more than one significant digit, because otherwise there's only 10 possible answers, you know. So if the answer comes out as 27, if I say 6 times 4, I want you to put down 24, not 20. Because 6 4s are 24. Yeah, if it really is a measurement of 6 times a measurement of 4, in measurement terms, I've got to round it either to 30 or 20, because I can only have one significant figure. But that's for the lab. That's not for here. So, but man, people get so upset. So, what about doing sums on these things? Well, basically, when we do sums on these things, so that first of all, that's a typo. So that should say 26. When we do these things, there's 2 rules. If you're multiplying and dividing, your answer should have the same number of significant digits as the worst of your 2 or 3 or 4 or 5 numbers you're multiplying. Your precision of your answer is limited by the precision of the worst thing you've got. If you're adding and subtracting, your answer should have the same number of decimal places as the worst. It's a different rule. I can justify it. If I go 12.3, 2.1, let's do our old long multiplication. 2, 1, 6, 4, 2. Add them up. 3, 8, 5, 2. So I've got that. That's my numerical answer, yes? Everybody with me? Let's change colour ink so we can see this. That's an uncertain 1 and that's an uncertain 3. We agreed on that because they're measurements. So that means that, well, man, uncertain 1, that must be an uncertain 3. Uncertain 1 by a certain 2 is uncertain. Uncertain 1 by an uncertain 1 is by a certain 1 is uncertain. All those are uncertain. And the 2 by the 3, that 6 is uncertain. 2 by 2, that's a certain 4. So that's an uncertain, and an uncertain. How many uncertain digits am I allowed to have? How many guesstimations am I allowed to have? 1 digit. I got 3. I got to round until I get 1. So that goes to 26, whatever it is. So it follows the rule. That was 2 significant digits. That was 3 significant digits. My answer has 2 significant digits. That's the rule, but there's the logic behind the rule. And this 1, 2, 3, 5.35. Let me just have a quick mind thing and see if I can actually improve this a little bit. Yes, I'm going to get rid of you. The reason why I'm doing that is because, well, you'll see in a minute. So I add these guys up and I go 3.128. Is that right? Just adding them up, yeah? That's an uncertain 3 and that's an uncertain 3. So that's an uncertain 3 and that's an uncertain 8. And how many decimal, how many guesstimation columns am I allowed? 1. So I can only have this, so that goes 1, 2, 8. And if you look at it, if I went by the number of significant figures, then I should have 2 in my answer. So it's not working by significant figures anymore. It's working by Oh, no decimal places, one decimal place. I have no decimal places. So you just learn the two rules. Multiplying and dividing, you're going to use significant digits. Adding or subtracting, use decimal places. Whatever's worst in the original numbers, it works nicely. So on that previous example, 22 divided by 7, well, I'm dividing, my answer's 3 meters per second. I round down to 3. I shouldn't say it to any more precision than that. I should get a better ruler, and I should get a better clock. Factor label. We all know how to do conversion factors. You just use the conversion factor. But we get them wrong sometimes. And what people do is they get the conversion factor upside down. So it's not that we don't know how to do it, it's just that we need a methodology to do it right easily. This is the methodology. My chemistry buddy showed me this, and it's just beautiful. 3 pecks per dross. Oh my word. 3 peck. Per means over. Dross means 1 dross. Don't even know what they are. I want to go to meters per second. First conversion factor. 1 meter equals 6 pecks. Pecks are on top. I want to cancel. Math still applies. I want to cancel pecks out. Put pecks underneath because that's how you cancel. Meter and pecks. Meters has to go on top. Cross, 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 cross. 1 meter equals 6 pecks. So I'm part of the way there. I want to get rid of my dross. Dross is on the bottom. You want to cancel out, you've got to put dross on top. That means that your seconds must go on the bottom. 1 dross equals 5 seconds. Dross, 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 dross. 3 over 30, which equals 0.1 meters per second. Piece of cake. Just lay it out and you'll never get them wrong. If you do it in your head, I swear, Albert Einstein would get them wrong on tests sometimes if he does them in his head. And he'd be really ticked off, but he wouldn't get the points. So just don't risk it. Just, lay it out. Final little bit. And I do mean this. So when I came back into teaching, I don't know if I told you, I got several classes, and you're never sure whether you said it to one class or another class. When I came back into teaching, I'd been in industry for about 15 years. I'd been doing research before then. I knew how to do this stuff. I hadn't practiced it in a while, but I knew how to do this stuff. And so I'd come in and go over the homework, and I'd make slips. I'd catch them, but I'd make them. And so my answer became like this minefield full of crossings out and the like. And after about, I'm new to the school, so the students don't know me, and after about 2 weeks, this female student, I think rather bravely, turned around to me and said, "Do you mind not going over the homework in class today?" And I said, "Why would you not want me to go over the homework?" And I think this took guts. She turned around to me and said, "Because I do the homework, and I think I understand it, and then you explain it, and I am totally lost." And it was a real one of those gut-wrenching moments where, man, that's cutting close to the bone. And so I had to kind of go home and sort of think, I can't go on like this. I mean, I'm going to lose the confidence in the class. And once you lose it, you're not going to get it back. You've got to wait for the next class to come. And that's one of the problems. And I know why they're saying it. I know why she's saying it, because it's like I'm doing crossings and turning arounds. And, oh, really? Let's think about that. Do I go home and learn every homework question before class so that... No, I got to find a way that I make fewer slips. It's not that I can't do it, it's that I'm making slips because my thinking's not systemized. And so I sat down and started thinking about how to do it. And I went back and I thought back about what I was taught. I didn't invent this. I was taught it and just, who cares? As long as I get the right answer, who cares? And yet, it's harder work if you don't approach it in a good way. So this is me as your coach saying, this is how you improve your serve. You know, you can serve, but I'm trying to tell you how to improve it. And it's style, it's form. And the way you do it is this. Number one, you picture the word problem in your mind. If it's got a merry-go-round on it, you picture a merry-go-round. If it's got a ramp, you have to picture a ramp. And then you draw a diagram. And if you're not good at drawing diagrams, join the club, practice, and you will get better. Just get yourself a little protractor and draw it carefully to begin with. Within a couple of weeks, you'll be better. But a good diagram will save you, and a bad diagram will cause problems. No diagram, and I can trick you so easily. I can have the signs will be all wrong. You'll be going backwards. So you've got to be able to draw a diagram. If you don't know how to draw a diagram, that's a real telltale that you don't understand the word problem. And that's an issue. That's as big as not knowing how to do calculus. That's huge. So if you can't draw a diagram, really watch out for it. And then list all the parameters. You know, I'm given a mass, I'm given a distance, I'm given a time. List them. And especially because you guys don't have equation sheets, that's jogging your memory. That's getting you ready. And don't forget to put down the unknown. One time I was stuck scratching my head and I couldn't solve it because I didn't know an equation that had these things in there. I forgot to put down what I'm asked for. You know, it was like I had M and I had A, and I forgot to put down what F is. I didn't know an equation with M and A. Well, F equals MA, you know. So put down what you're looking for. And I'll tell you, especially at the beginning, our kind of problems are such that it really helps. Eventually we'll get to F equals MA, and we might not list the parameters. Fine. But I'll tell you, in physics too, you can for sure tell when I'm scratching my head kind of going, oh, what's this equation again? Because I'm listing parameters. It's my fallback. Whenever I'm feeling uncomfortable, I list parameters. As a rule, I'll also list them in these first few chapters because they are complicated questions in terms of the numbers of things you're given. So list your parameters. And then you kind of go, what equation links these parameters? I will sometimes give you extra stuff. And so it's not that there's only one equation. You've got to think about the equation. Maybe I'm giving you something that's completely irrelevant. So pick your equation. Substitute numbers in. We're finally at math. Substitute numbers in. Work out an answer. Ask yourself, does this make sense? The math is the last little bit. All the physics is in front. So many times I'll see students do correct math on completely the wrong problem. Because their math is fine. This is not a math class. Their physics is not good because they're not visualizing. So if you do this, if you practice this, if you look at the videos that are online and say, how is he laying it out? It's what helped me go from making unacceptable numbers of slips when I was nervous to making relatively few slips when I'm nervous. When am I nervous? When I'm doing a problem in front of you, especially a new class, we don't know each other. That's when I feel it. When are you nervous? Homework? When are you kind of like on edge when you're doing physics stuff? In a test. You might not make any slips at home, but if your technique's not good, you'll make slips on a test and you go, oh man, but you know, you lost points. So, you know, don't reinvent the wheel. You know, I mean this, it will help you. So slow down, write all the steps, and it will get better. do stuff in your head, put a few numbers down, get an answer. Yeah, maybe you'll get it right. But if you get it wrong, you've lost everything. When I grade, I look for the diagram, I look for the equation. What numbers did you substitute in? What's your answer? If most of it's right, I can give you some credit. If it's just an answer that's wrong, I can't give you anything for that. So slow down. It's not multiple choice technique. It's open question technique, and it's slightly different. Okay? So next time, I'll see you next time. Don't forget quiz next time. So the quiz is going to be on prefixes. We're going to focus on prefixes. 3 easy points.